Hey everyone! So on the note card, some people were confused about the natural abundance. So I'd like to take some time and walk you through how to approach natural abundance problems. So in this case, we have 4 isotopes of sulfur. We have their mass in AMU here, and then finally the percent abundance. And so the way that we would approach a natural abundance problem is we would want to find the weighted average, where we take the mass of the isotope times the fraction or the mole fraction of the fractional version of the percent of that isotope, which will represent by A here. And so to get the fractional version of the percentage, we would divide these values by 100, so 0.9493 for 32, 0.0076 for 33, 0.0429 for 34S, and then 0.0002 for 36S. So in the way we would approach calculating the weighted average for sulfur is we would have the mass of 32S, so 31.972 AMU times its natural abundance, the fractional version of its natural abundance, which is 0.9493, plus the weighted contribution of 33S, so its molecular weight, or atomic weight, so 32.971 times its fractional abundance, so 0.0076, plus the contribution from 34S, which would be 33.968 times 0.0429, finally plus 36S's contribution. So let's erase that there. Or 35.967 times 0.0002. So if we take a minute, we solve that out on a calculator. We get a value of 32.066. Now, how do I know if that's the correct value? I go to my periodic table, which I've got over here off screen. I look for sulfur, and I see that sulfur is listed as having an average atomic mass of 32.06. All right, looks like I'm on track. So that's the baseline for how we would calculate an atomic mass when we know the masses and relative contributions or relative abundances of the different isotopes. Today, we solved a very different type of problem. And that was where we looked at two isotopes of the atom bromine. And so it was a case, so for bromine, if you look up on the periodic table, bromine has a mass in AMU of 79.904. And we know that the two isotopes of bromine differ by 2 neutrons. And so differ by 2 neutrons, and there's the relative of abundance of each is about 50%. So there's a very specific way in which I would recommend that you approach this problem, although you all were very quick and clever to figure out the relative masses of each based off of the periodic table. But here's how you would work it out the long way and how you would approach it if you were given a percentage that wasn't quite so straightforward as 50%. So what we know, so if we pull in the equation from that we just started for sulfur, we would know that the mass of isotope A, if we start off with what we know, we know that the abundance of isotope A is equal to the abundance of isotope B, which is equal to 50%. And then we know if we take the mass of A times the abundance of A plus the mass of B times the abundance of B, we get a weighted atomic mass of 79.904 AMU. Now, knowing what we know about the two isotopes being separated by 2 neutrons and the relative abundance, we can start doing some simplifications to get an answer out. So we know that the mass of A is equal to the mass of B, which is about 0.5, which is around 0.5. We also know that the mass of B is equal to the mass of A plus 2 AMU. Because again, one of our isotopes is bigger than the other by 2 neutrons, which means we're bigger by about 2 AMU, or 2 AMU and some very small change. And so we can set up here as we can say, okay, the mass of A times the abundance of A plus the mass of B, which we know to be the mass of A plus 2 neutrons, or 2 AMU, times the abundance of A equals 79.904 AMU. So what we've done here is by putting in those substitutions, we've put our equation in terms of A, so we can solve for A and then back calculate for what B should be. So if we do some algebra here, we can pull out the abundance of A, and then we get MA plus 2 is equal to 79.904. Now, we know that the abundance of A is equal to 0.5 because whenever we're doing these abundances, we're going to be doing our percentages in terms of fractions. So the mass of A, or 2 times the mass of A, because we're adding those two together, plus 2 is equal to 79.904 divided by 0.5, or 2MA plus 2 is equal to 159.8. Now we can subtract 2, so 2MA is equal to 157.8. We divide both sides by 2, and then we get that the mass of A is equal to 78.9. Okay, so you know that the mass of A is 78.9 AMU. Now, the mass of B is equal to 78.9 plus 2 AMU, because again, there's a 2 neutron difference between these two isotopes. So that means the mass of B would be 80.9 AMU. Now, we know that we don't, and so when we look at our mass numbers, we don't have fractional neutrons or fractional protons, so in this case, we would round them both up. So isotope A, so bromine A, would be 79, have a mass number of 79, and our isotope B of bromine would have a mass number of 81. And so that's the way that we would approach isotopic or average isotopic atomic mass from 2 different perspectives of the problem.